And let me get my title slide up there. Here we go. We're ready to go.
Okay. All right, welcome everybody. I'm going to do a brief intro of my friend Chris Bystroff. We have sort of weird parallels in our lives, and then we met late in life through Dave Gardner, who does the Growth Busters podcast down in Colorado Springs, and we're going to go do a podcast with Dave Gardner tomorrow with Growth Busters. Chris got a bachelor's degree in chemistry from some obscure college in Minnesota. Carleton, is that right? Chemistry, and I got my bachelor's degree in chemistry from an obscure college in New York, and we both came from California, and he went on to do a PhD at the University of California in San Diego in chemistry, and I wandered around aimlessly and ended up getting a PhD at UC Santa Barbara in geography. But our interests have converged on this limits to growth. You guys are probably aware there's a 50-year anniversary of limits to growth. 1922, limits to growth, 1972. Both of us are, sort of neo-Malthusian nutbags about 8 billion people on the planet, adding 80 million more every year. Chris became a professor in the Department of Biological Sciences. He just gave a lecture in my population class that involved like protein folding, molecules, antigens, etc. His day job is inventing vaccines, and he is working on a vaccine that is a way it's a contraceptive vaccine that's reversible, right? So most of his day work is in lab with CRISPRs and PCRs and all that kind of stuff. And so on the side, he does other things like overpopulation questions and modeling population. So he did his PhD at UC San Diego. He's done a Fulbright in Nicaragua. He did X-ray crystallography, and now he does biomathematics or something like that. I think this talk will be very interesting. It's a great, I think, talk for the 50-year anniversary of the Limits to Growth, and I will ask you to welcome Chris Bystroff.
Thank you very much. Oh, you didn't mention we might be related. My mother's maiden name is Sutton.
Oh yeah, what's going to be your name?
Thank you for having me. It's an honor to be here. I love talking about this topic, but it's not a topic everybody loves to hear about, so I start off with the sinking ship slide. Love it. It's the feeling you get when you talk about this topic. And you gotta address the feeling, because otherwise that's what you're gonna be thinking about. It's not doomsday, but it does give you this sinking feeling. And I believe that any problem, no matter how big, is not gonna go away if you don't talk about it. So we have to talk about the sinking thing, and it's not as dire as you might think. So we're gonna talk about this. Population going back 1,000 years has been growing, but not exponentially. It's been growing beyond exponentially. The way you know that a curve is super exponential is that the doubling time changes. And if you look at the doubling time in 1500, it was 700 years. At that point, if it continued, we'd be nowhere near the 8 billion that we're currently at. But it accelerated when population reached 1 billion, the doubling time reached 260. When it reached 2 billion, the doubling time reached 125. If we continued at that exponential growth rate, one more doubling time would put us at 4 billion only in a few years. But we are way beyond that. Doubling time reached a maximum between 1950 and 1987 when we went from 2.5 billion to 5 billion, and since then it's been slowing down. So my interest in this, I don't know if I want to give you my origin story, but I've just always been interested in this. It's always been weird to me. And I thought, the only way you can get any serious attention is to try and publish something. And I'm a math guy. So I figured, well, let me see if I could fit this equation. It was harder than I thought. A naive first fit is you try to fit it to the best fit exponential growth curve with a standard fixed doubling time. That's the best fit. It's not a very good fit. So I looked in the literature. I found out somebody's tried to fit it to a hyperbola already. Hyperbola, by the way, makes no sense at all because it reaches infinity. And there is a paper published in 1960 when I was born, which fit population up to that point to a hyperbola and predicted we would reach infinite population November 13th, 2026. And it fit very nicely, and not only that, but it tracked population pretty well up to the 1980s. So, but it made no sense. But you could fit lots of other equations that have very steep curves. Population in the 20th century fits well to an equation I call the hyperexponential equation, which is an exponent of an exponent. But that fit doesn't go back very far. But all you have to do is combine exponential fit and hyperexponential fit, and lo and behold, it fits population very nicely. This is very suggestive of something. It's like the Earth is a one-pot experiment. It's I don't know. We have some kind of self-leveling effect across the planet. And maybe that's called migration. So one way or another, we're growing at what turns out to be a very predictable rate. Hyperexponential growth is e to the x, where the x has some constant times time. So the exponent of an e to the x equation is related to the doubling time. It's the rate. It's actually log 2 over the doubling time, which is the rate. And so if I take e to the x, I'm talking about something that is doubling with an increasingly fast rate, and that rate is going up exponentially. That's the equation that fits. The way that I could make sense of that, because the process was first fit it to equations, then make sense of it. I couldn't make any sense of a hyperbola. But this equation made some sense. Thinking about it, I go, well, the rate must be a function of something. And the thing that I thought was a function of, and I don't know if I have it on the slide, is technology. I think I blacked out that slide. But technology, broadly defined, are things which make you live longer, and also things that make you consume more. So, and technology, you could also say, is knowledge, and knowledge tends to build on itself. I mean, we all new inventions are standing on the shoulders of giants. Is that what they say? You know, technology builds on technology, and things that grow in proportion to themselves are exponentially growing things. And so the thing in the exponent is, in my interpretation, technology, and it's growing exponentially. And then the rate of human growth is proportional to that technology. It's analogous. You have to look for analogies in the real world, and they're hard to find, but one of them is the spread of a fire in an enclosed space. That's super exponential. The reason fire in an enclosed space is super exponential is because the flame, things burn faster if they're warmer, and the fire heats it up. And so the growth of the fire, growing in proportion to itself, it grows even faster because it's heating up its fuel. Unfortunately, it reaches a point where it dies. And that also might be part of an analogy of human population growth, because the depletion of oxygen and the fuel could be analogous to depletion of resources on the planet, which, as you know, are finite. So this is kind of a model for what that I wanted to, this was the starting model for something that I developed. So hyperexponential growth ended about 40 years ago. If you take the mathematical best fit of population up to the latest census, which at the time was 2010, it deviates starting around 1980. So here in the thick blue line are census data. In the dashed red line is the best fit hyper-exponential growth model. I can't get it to fit. If I force it to fit more recent data, it doesn't fit prior data. So this is the best fit I can come up with, and it deviates by going on 2 billion high. So, and this is the fit over the last 2,000 years. Hyper-exponential plus exponential fits all the 2,000 years of data pretty well. Census data gets noisier as you go further back, but it still fits it. So, so something's going on. We have hyper and exponential growth driven by technology pushing population up, and then since 1980, something else must be pushing it down. We want to keep the model simple. There isn't some simple switch that's happening. It must be something that's always been happening or always been possible, but is now being felt. Can you think of what that thing could be that is pushing population down, getting it to grow slower than technology-driven hyper-exponential growth would predict? That's the modeling challenge. If we look at what's happened in the last few decades, this is data from where? Census.gov. A lot of regions of the world and subpopulations are no longer growing with a positive second derivative. They're curving downward, not upward. It's hard to detect unless you do the three-point test and see whether it's curving up or curving down. But the whole world is now past the inflection point, and the US is well past the inflection point. India is past the inflection point. China is already probably going down. So we're past the inflection point of growth. The next change in curvature is downward curvature. So previous predictions and projections forward all predict that eventually it's going to level off and even go down. But these predictions might have some problems with them. The UN predictions are done by not by biologists, not by geographers, not by ecologists, but by economists. And they're extrapolations. They look at the trends in the birth rate and the death rate, and they have a stochastic model for immigration, and they think if you migrate into the system, you kind of adopt that birth rate. And they're going up slowly. Two other institutes have competing predictions for the population going up to the end of this century, and they disagree. One of them involves experts coming up with causal relationships, which they can kind of understand. So establishing some kind of population underpinnings and then using that to get a number for population. And one of them is just called an expert judgment model, where you kind of average expert predictions. Both of those are very much on the low end of what the UN predictions are. All of these models ignore the environment. All of these models ignore the Earth. They ignore the finiteness of the Earth. There is no resource limitation. Now, it might have come in the expert model. The expert models may have used that, but nothing explicitly about the finiteness of the planets is included in this model. So to me, when that happens, you go, well, there must be a room for another model. I looked at what assumptions did go into the model, and the UN model, the first author is Wolfgang Lutz, this guy. And I wondered if he was assuming something, and sure enough, if you look into the methods section of the paper, he was assuming logistic growth. Logistic growth means that there's some magical attractor, some carrying capacity at which the population grows up to. And if you look in the methods, he says, beyond 2030, 2035, fertility was assumed to reach an average level of between 1.7 and 2.1 children. So something around replacement value. So there was assumed to be some kind of final fertility that we were going to converge upon. That's like a logistic model. Furthermore, in the methods, he says the range for life expectancy increases after 2030, 2035 was set to be 0 to 2 years per decade. In other words, always going up or staying the same. So these are built into the model. You can't have a model that peaks and goes down very easily if you assume life expectancy is always going up. So I claim flaws in the model, room for improvement. What can we do? So as a biologist, I'm going to go with simplifying assumptions that agree with what biologists say about human population growth. In other words, that we are K-selected species. I'm taking an image directly from a biology textbook, an ecology textbook. There are R-selected species whose population growth is determined by predation, and there are K-selected species whose population growth are determined by carrying capacity. I don't know how they got K from carrying capacity, but that's what they did. This agrees with Thomas Malthus, late 19th century cleric and population watcher, philosopher, who said that species grow to the level of subsistence. Thomas Malthus's work spawned Charles Darwin's work, and he used this idea of exponential growth limited by carrying capacity to explain how we got natural selection. You had to have a superabundance of reproduction in order to have survival of the fittest. So Thomas Malthus's philosophy was science, really. He was talking about K-selected species. And there we are, humans, the poster boy of K-selected species. So we have a simplifying assumption. We're a K-selected species. And you could ask a question. What's going to happen? We have seen population go up. Is it going to stay up? Or is it, as the UN model predicts, go down gradually? Or is it just going to go down? I'll simplify it. It's either going to stay up or is it going to go down? And if it stays up, if we adopt the K-selected species simplifying assumption, we are asserting that the carrying capacity is flat. And if it goes down, again, because the assumption is we're a K-selected species, if population goes down, it must mean that the carrying capacity is going down. And so Malthus said, you have to model the carrying capacity. You have to model the limits. Malthus, I gave a talk about Malthus a little while ago, so I had to borrow some slides for my own talk. Yeah, Malthus was a smart guy. And he's not the doomsday guy that he's made out to be. The popular use of the term is not really accurate to what he wrote. What he wrote is that when population gets above that level, he calls the level of subsistence, you can translate that to carrying capacity, that checks kick in. And checks in his writings are classified preventive checks and positive checks. And positive checks are the ones that get all the attention, the 4 horsemen of the apocalypse. I think there's 4. But probably most of what's happening is preventative, I hope. And maybe some of the more mild of the positive checks. Malthus's work, the majority of it is him documenting all the ways in which societies control their population or are controlled in regions and countries throughout the world, including places in South Pacific where population is actually controlled by homicide, and Norway, where population is controlled by putting men into the army when they're at their peak reproductive age. And in England, he talked about the death rate being higher under the stress of overpopulation because of overwork, because of poverty, and the subtle effect that has on your life expectancy. He talked about these things. The preventative checks can be further classified as moral restraint, which is what all the clerics of the day are promoting, and what they call vice. And contraception, abortion, and infanticide fell into the category of vice, and abortion was considered like infanticide, I think, at the time. So these are the forces that are acting to make us K-selected species. Some of them sort of psychological. Some of them are the environment imposing itself on you. Positive and preventative checks. So with this view, let's look at what is the Earth imposing on us. At the time that Malthus was talking, he was looking at individual regions of the world. But since then, we've really become more global. So we have to talk about not regional, not local limits, but global limits. So what are they, and are we approaching them? First one I could point to is groundwater. If you ever fly across the country and look down as you're coming through the flyover states, like this one, you see circles. And those circles are farms that use center pivot groundwater irrigation. And they have this irrigation system that travels around on this big arm, 1 kilometer long sometimes. And that's where the green is for a while. And then you fly over states, a few years later you'll see brown places where there's a circle there. I've seen them in Nevada. Nevada, they've sucked the groundwater dry in these places. And on the right you see the Ogallala aquifer extending over much of the Midwest, and the depths of those they update periodically, and in this layover you'll see the changes in the depth, and wherever it's red, like down here in Texas and Oklahoma and Kansas, is where it's in decline, and that teaches us that the replenishment rate of this aquifer is much less than the extraction rate. So water's being depleted from the major aquifers of the world. Looking at California, which is periodically, chronically in drought, aquifers are many of them are in decline. If you look carefully, you see some of them here are green. They're actually replenishing, but a lot of them are red, especially in the southern San Joaquin Valley. Nationally, you can look at the largest aquifers, and of the 37 largest aquifers, 21 of them are currently in depletion. So we're using water at an unsustainable level. You can't grow food without water, and a lot of places will not support food unless you irrigate. So that's a limit. It's a limit to growth because the amount of sustenance that we can produce is depending on how much water you currently have. Another limit to growth, of course, is the land. There's the total amount of arable land is obviously finite, unless we could find some way to create new islands and farm those. But I can kind of just discount that. I don't think we could do that much. And it's also limited by the fertility of the land. And if you assert that we can always just use additives to make any land fertile, we can fertilize the desert, then there are other limits that come into play that involving how sustainable that is, which I won't go into. A lot of our calories come from the ocean, and there's been predictions by Richard Ellis in his book, The Empty Ocean, that all major ocean fisheries would be commercially extinct by, he said, 2048, which happened to be 50 years after he wrote the book, because we're doing massive industrial scale fishing. We're using these gigantic purse seine nets where you drive the boat in a big, huge circle and then you just pull it together like a big purse. That's what you're seeing here. And it's driving fish into commercial extinction. An example is the Canadian cod fisheries have went into a commercial extinction in the 1990s. Now you can still go out and you can find cod, but cod used to be 6 feet long and now they're little 1 foot guys. It's not worth the trouble. Habitat. This is a image that where they've taken numbers for land mammals by weight, and the gray ones are the ones that fall within the domesticated class, and green are ones that are in the wild. And you might think wild species are unimportant, but there's a lot we don't know about what kind of services they are providing us. And so I think there's a case for wild species being a limit. There might be some service that they're providing us that we can't live without. Another sense ecosystem services are limits to growth is that ecosystem services maintain a stable climate, and our current carrying capacity depends on maintaining the same climate year to year. So plants, including the crops that we depend on, all have evolved with the same timings and nutrients year to year. And now we have mega droughts, now we have more fires, we have more storms and more flooding, which means that the environment for growth is more erratic, which means that the carrying capacity of that is decreased. So that's another limit to growth. That sounds like it's complicated and hard to put into a mathematical model, so we're going to have to simplify. Also, humans can't continue getting older and older. We have some pre-programmed lifespan. There's some studies in other animals where their lifespans have programmed death, programmed cell death, and you never see 200-year-old humans, so there must be some mechanism by which our lifespans are limited. So you can't just extrapolate. You can't assume life expectancy will constantly go up. So how do we model the limits to growth? Do we make it static or do we make it dynamic? I've made an argument that it must be dynamic. So that makes the problem harder. But you could simplify as much as you want, but you can't simplify away the truth. So we have to look at how you'd model something that's dynamic. The tools of the trade is systems dynamics. I use a system called Insight Maker. I also use Image Maker, but Insight Maker. And Insight Maker, this is that thing in the middle there is a shot from Insight Maker. This thing? I'll just point on here. In the rectangles are quantities, and in systems dynamic these are called stocks. The arrows are flows, and so that's decrease or increase of the stock, and then the thinner lines are dependencies or variables. And you could make an arbitrarily complex system using these components, these primitives. And this example here is a Lotka-Volterra model where you depending on what you set these values, alpha, beta, gamma, delta to, you can get different types of oscillation, including damped oscillation, expanding oscillation. So it's a great method for exploring different relationships. Going back to Malthus, he proposed that when population went past the carrying capacity, in his words, the limits of subsistence, it would be pulled back to it. And so he said that he would expect in populations there would be oscillation around the carrying capacity. And that's just a clip from a biography of Malthus that was written around 1890. So summarized here, if population goes up, that's going to mean cost of living goes up. The reason for that is standard economic models that shortage leads to increased cost of living. If cost of living goes up, birth rate goes down. Now that causal relationship may be questioned, but it's an observation. As it's more expensive to have kids, women choose to have fewer kids. If you have fewer kids, population goes down. That's oscillation. If population goes down, well, there's more resources. Standard classical economics says more resources, prices go down, cost of living goes down. Now, back to women, and they're deciding the family size, they go, oh, I can afford to have another baby. Birth rate goes up, population goes up. So Malthus's causal relationships create an oscillation. And he pointed that out way back in 1800. So this is the goal now, to take that and put it into a model. So here's my attempt. I'm going to start with population as a stock. We're going to have birth rate and death rate as the flows in and out. We have dependencies. Population determines birth rate and death rate. And then we have food as a short for subsistence or carrying capacity. And that has flows, production and consumption going in. Production depends somehow on population. Consumption also depends on population. One of the things that Malthus says is that, and production also depends on a finite quantity. I'll call it available land, but there are a lot of limits. That's just one. And Malthus, no, I forget, I'm not done with the animations yet. Food also has an effect on the birth rate, it turns out. And food has a negative effect on the death rate. The little line there means negative effect. That is, the depletion of food increases the death rate, obviously. So Malthus said that production can be increased with population in a linear, he used the term arithmetic relationship, whereas consumption goes up exponentially because population grows in proportion to itself. These are then assumed constraints on how you model production and consumption. It might be even less than linear. In his writing, he says it's even optimistic to say that production can go up linearly. I think it goes up probably logistically. But so then what we expect to happen in this model is an oscillation. As consumption is less than production, population goes up. If consumption is more than production, it goes down. So do we see those actual oscillations? Well, the final fit of the model that I generated is here now in black, and in red are census data. And you kind of, if you squint, see something that looks like an oscillation, where in the early 20th century, the model predicts a higher population than we saw. And in that early 20th century, we had world wars, we had the Spanish flu, we had some of Malthus's misery kicking in. And then we saw a population increase, the baby boom in the 50s and 60s, and then we saw it going above what my model predicts. So if you squint, you see some oscillations in there. Malthus predicted that these oscillations would probably not be so obvious to the common view anyway. So I'm not the first to use systems dynamics. I teach a course called Human Population, and this is the book that we use. And right on the front of the book, it has the results of simulation by their model called World4. And the yellow line is population, and the red line here is resources, so nature. And so you see that going down, and then population going down after that. Their model is very complex. My first inclination was to go to this Donella Meadows model, World4, and just see if I could find ways to improve upon it. But it was a hard task because it's a very complex model. So this is what World4 looks like when you put it into Insight Maker. Okay, so World4 does a prediction which we can contrast with the UN's predictions. World4 now does include limits, and you see that it predicts a peak around 2040, 2050, and then a decline to something like half of maximum. So now I started in saying, can I make it much more simple? Because I'm lazy. I don't want to deal with 126 different flows and stocks. Can I deal with just a very simple one, very, very simple model? And so I'm doing, and I called it World4, and I emailed Dennis Meadows and I said, can I call my model World4? And he says, I can't stop you. So I called it that. There's 4 stalks. Each of them is called a closed system, so they sum to 1. One of them, you notice population is not one of them. One of them is biocapacity of the planet, and I just use it environment. And the environment sums to 1, and it's composed of ecosphere and human sphere. Human sphere defined as the biocapacity that is domesticated, and ecosphere as the biocapacity of the planet that is wild. And then because I am assuming technology-driven growth, I have to have something about technology in there, and I've been working on what the right terms are for low and high technology, and just settled on just using the words low and high. You could call it high being knowledge and low being ignorance. You could call high being less mortality and low being higher mortality. But let's just say, call it low technology and high technology, and then, and for simplicity, have that sum to 1. Then going from low technology to high technology we'll call learning, and it is possible to go from a high technology world back to a low technology if the technology no longer works for the current system. So obsolescence is that flow, and that would happen if, like, climate change made the current farming methods obsolete. So even though those tractors and those combines still exist, maybe they don't work anymore. So that's going backwards in technology. Going from ecosphere to human sphere is the birth rate. We can call it domestication because of the way that those 2 stalks are defined in terms of land. So that's land now being farmed or now being used for disposal of waste or something. And then going backward is rewilding. And the dependency, I should be doing my animations because I've been talking about them. Yeah, so, the dependencies are that low technology has to have some effect on the death rate. When humans die, the amount of biocapacity that they needed to survive is now available, so it becomes rewilded. And the rate of that is depending on something, on mortality. So the low end of this technology closed system, examples of what that represents would be increased predators, increased storms, increased disease, unrest and violence, and hunger. Whereas on the high end, high technology represents things which increase the life expectancy, decrease infant mortality, and that's medicine, machines that make it easier to get more food, laws which keep the peace, communication that allows us to trade farther and farther away and maintain a stable food supply, and trade, yes. And the ecosphere, human sphere idea is derived from the ecological footprint literature. And so hope I'm sticking pretty much to the way they conceptualize ecosphere and human sphere. Ecosphere is anything that is not domesticated, not controlled. Fresh water, for example, humans don't really create fresh water. I'll get to an exception in a minute. Fossil fuels, we don't create that. So believe it or not, that's ecosphere. That's wild. Fossil fuels are wild. Ores, unprocessed ores, are part of the ecosystem. Climate stability is a service that is not domesticated. It's not something that we have found a substitute for, so it's wild. Carbon sequestration, it's carried out by trees. We don't have a way to do it, so it's part of the wild. Pollination, we're not going around with paintbrushes pollinating squash, so that falls into that category too, and so on. And on the human sphere side, it's not just cities and such, it's anything, any land that is now domesticated, used primarily for human survival. It's recycling, so any metals that we now take charge of are part of the human sphere. Any technology that we use to generate energy is part of the human sphere. Desalination is the exception I mentioned about fresh water that is within the human sphere. So these are examples of what is represented by the very simple model. And I resist the temptation to make the model more complex and to split it out into all these things, separate measurements. But it makes something hard. It makes it hard to fit the model and test the model to see if it's right, because each of these quantities is actually the sum of a whole bunch of things. It's an aggregate. So I haven't figured that one out yet. What one point of this model is that the population is not an input but an output, and this derives from the assumption that we are a case-selected species. So you don't have to really work with birth rate and death rate. All you have to do is figure out what the carrying capacity is, and the population is derived from that. So population, CC is carrying capacity. Population is defined as the human sphere multiplied by the carrying capacity equals population, because human sphere is measured in hectares. Carrying capacity is measured in humans per hectare. So if you multiply those together, you get human numbers. So it's a readout. Reviewers gave me a hard time for that. So this is based on ideas that are not new. Mathis Wackernackle and Bill Rees, among others, have written extensively about the ecological footprint, and they, in their book, conceptualize the world, simplify the world into human sphere and ecosphere in a similar way. But so that's the features of this new model called World4. Growth is driven by technology. Population is limited by the environment. So let's look at its properties. It carries out the oscillation that Malthus predicted should be happening. Here's the causal relationships. Population increase should lead to the loss of ecosphere. The loss of ecosphere means the loss of ecological services, which means climate change. Climate change leads to decreased food supply because of the lack of stability and the obsolescence of current farming technology. Decreased food supply leads to population decline, and therefore you have an oscillation. So in the model, let's see. So we will get oscillation. So where's my animation? So as human sphere goes up, ecosphere goes down because they sum to 1. As ecosphere goes down, ecological services go down, therefore climate stability goes down. As climate stability goes down, technology becomes more obsolescent. You no longer can get the same amount of food production with the current technology. And so that in my model means low tech goes up. I don't know if that makes sense. More loss of technology goes up. And then that means that since technology relates to human carrying capacity, means that human sphere goes down. If human sphere goes down, because they sum to 1, ecosphere goes up. The ecosphere is rewilded. If it's rewilded, I don't know how long it takes, but eventually it should lead to climate stability. This is a bug in the model. I don't know what the delay is there. If climate stability goes up, that should make it easier to produce food in larger quantities. So we'll go to higher technology. Higher technology then leads to increase in human sphere, and it goes on and on, up and down. But do we really predict that humans are going to behave like a Volterra model and just go up and down, where the predator is Earth, I guess, and we are the prey? maybe not. And the reason for it not really being likely to do that is that human sphere, unlike an R-selected species that's controlled by predation, human sphere should grow exponentially. And so it depends on itself, so you have to have an arrow going back to itself. Moreover, because we have made the assumption that this is technology-driven growth and technology grows intrinsically, then you have to put into the model that high-tech and low-tech, which sum to 1, and high-tech builds on itself. High-tech drives itself. If you do that, then, and you run the model, you get 1.5 oscillations. This is called a damped oscillation. Therefore, the model is going to spit out a damped oscillation. It's going to go up, down, and then just kind of level off. So that's baked in. That's, if you put those assumptions into the model, we're going to get a damped oscillation. That's not mysterious where that came from. I didn't discover it. It was built into the model. It's baked in. So to make a good prediction, as good as we can make given the limitations of the model, we do that by fitting. And so there are parameters of the model. There's, the degree, the parameters shown here. This is a parametric fit. This is a parametric exploration. And the fit to population data is in the color coding. Purple is a good fit, yellow is a bad fit. And this is parametric space. And these three, there are about 4 or 5 parameters to explore that are really not already fixed by literature data. And these 3 are E0, which is the total biocapacity of the planet. It's been published in Wackernagel's work, so I work with a range around that. And so that's one of them, but I'm treating it as an unknown anyway. The parameter which I called A is the relationship between wild ecosystem services and carrying capacity. And the other one, V, was the relationship between ecosystem services and obsolescence of technology. So they're just treated as unknowns. But what's built into the model is there is a relationship and also the equation that relates it, but the constants, the tuning is an unknown. So this was done by running lots and lots of simulations and then looking at how well that fits historical census data. Here's some examples. Now the equations can be extrapolated forward, and as they go forward, you're depleting ecosystem, therefore you're causing technology to go obsolescent, therefore your carrying capacity is going down, therefore population is going down. So, but which one of these is right? We don't know. They all fit. There's a lot of them that fit. Now that the 2020 census data is out, I can extend this data one more point, and I haven't made a slide. I think I did make a slide about what that does. Before doing that, this was the predictions going forward. So I didn't try to make it alarming, but this is what happens. So these are all random choices of parameters, and then culling, only selecting those parameters that fit historical data. So all these 100-something plots are superposed, including all the data from 1960 on, and you'll see they overlap perfectly there. That's because they were only included if they overlap perfectly. So if they reproduce historical census data, I keep them. Otherwise, I throw them away. But other than that, the parameters are chosen randomly. And then you look at the spread, and it's like, I don't know anything. I don't know where it's going at all. But the assumptions in the model tell me it's not going to be the UN projections. The UN projections are up here. This is LUTs. World4 is somewhere in between, and World4 predicts something like either stability or major disaster, the whole range. The peak is in a range which includes the past. I don't know what I want to say about that, except I guess it's possible. I didn't have the 2020 census data. Even with the 2020 census data, you don't know that it didn't peak and then 2020 is on the down curve, I suppose. Anyway, and the peak, and there's a 80% confidence region there for where the peak's going to be, and it's from 2017 to about 2030, somewhere along there. So that's why the population, the title of the paper includes "Global Population Will Peak Soon," and it's predicted to peak around, well, these. You know, we're now above that, so you could ignore all the things I say. But so this was without the 2020 data. An interesting thing happened, which is counterintuitive. The model says that if you take the total global biocapacity and you set it to a low value, the projected population will be high. Does that make sense? And if you set it to a high value, closer to what Mathis Wackernagel says, the results will be much more dire. We'll see a steeper collapse. How does that make sense? And so I thought about it a lot. And the sense of it made is that we don't know this number, but we see this population history. So if indeed the biocapacity of the planet is less than we expect, and we have been able to make it this far, then we're not really that close to the limit. But if the biocapacity of the planet is larger, then we have been using up more. We're using it up at a higher rate, and we're going to have a more severe collapse. This parameter turned out to be anti-correlated with the parameter that defines the feedback between ecosphere and ecosystem services. In order to fit the data with an assumption of a low, I hope I get this right, of a low global biocapacity, we had to assume that there was very little feedback between the loss of wild land and the loss of ecosystem services. You'd have to say that wildland must be really robust. And the other way around. If the reality is that the Earth is huge, we have a huge biocapacity, and it must be that it's pretty sensitive to the loss of wild land, and we're going to reach a tipping point early. And that's always, you know, those statements are statements based on the data that we have up to 2010. Don't have any future data. So these are what I call business as usual, BAU projections. There's no assumption of changes in policy. This is if we go forward without making any changes. But humans can make changes. So it doesn't have to be like this. So before I get to that, let me do this slide. So if the 2020 census, if I just take that data, business as usual projections, and now I look at the 2020 census data. When I made this slide, I didn't know that data, which just came out fairly recently, and I still can't find all the numbers that I want to find. It's very frustrating. But numbers were collected for April 2020. And now they're saying global population was in the order of 7.8 something billion. And it's going to reach 8 billion November this year. If it had turned out that in 2020 it was only 7 billion, which I was half thinking would happen, it would have meant that we were in for a steep decline. If, as it turned out, it's closer to 7.8 billion, we're in for a less steep decline. So this will be I don't know, my next paper. I don't know if I could publish this, but I'm thinking now it's less alarming than I previously thought. Okay, now moving on to E.O. Wilson. So if you now move away from a business as usual model, what can happen? There's a lot of things we can do, obviously. We can improve female empowerment. We can come up with a contraceptive vaccine. We can, improve awareness of ecosystem services. And we can have a future that's no longer business as usual. E.O. Wilson published, one of his last books was called Half Earth. And it's a call to action. It says that what we should do is preserve half of the world's biocapacity, make it wild. So ecosphere should be 50%. And he has in the kind of maps about where the lines should be drawn. So I tried tinkering with the model, moving away from business as usual. I hate to do that as a scientist, but part of me is an activist and says we gotta give guidance. And so what happens now if we try to reproduce E.O. Wilson's vision in the context of this technology-driven, resource-limited population model? Well, I modeled it by enforcing the 50% or whatever percent that I told it by increasing rewilding. So that's the flow back from human sphere to ecosphere, decreasing domestication. And I put it in a gradual phase-in of the policy. So you could play with the time the policy was started and the time that it took to phase it in, and the level of enforcement, the percentage that you want it to go to. And I found out that there's kind of a tipping point at about 43%. If you save at least 43%, then the curve looks very different than if you save less than 43%. And there's a few crossovers. There's some conditions in which it drops down and then comes back up. But basically, E.O. Wilson was right. If we save half the planet, we're not going to stay at the peak population. We're going to go down. It's too late now. But we're going to go down a lot less if we learn to save half the planet. And I think that's my message. Rewilding. The talk could go on, but it's 5 o'clock. And I have another talk called the Contraceptive Vaccine Project. But I'm not going to, I already gave that one earlier today. But that's my idea for how you would achieve rewilding. There's no other way but to decrease the birth rate. I think other ways are less humane. Thank you. This work was funded by the Grantham Foundation. Asked that their name not be explicitly attached to the work because they don't want to field all the flack, and also by the NIH. The contraceptive vaccine stuff is by the NIH. And I'll leave you with this quote from Martin Luther King. Unlike the plagues of the Dark Ages or contemporary diseases which we do not understand, the modern plague of overpopulation is soluble by means that we have discovered and with resources we possess. What is lacking is not sufficient knowledge of the solution, but universal consciousness of the gravity of the problem and the education of billions of people who are its victims. How many people knew MLK said that? And thank you. Questions?
Any questions for?
Yeah.
I was just a little curious as to the technology aspect of the model. Was that mostly focused on technology in agriculture, or did it also account for like technology in healthcare and things like that?
It was an aggregate, so it's very vague, but there's a definition of it that is what it represents is aggregate and vague, but it's very specifically a determinant of the death rate. So that is, technology is by definition the thing which extends life. So right? Medicine is that. Agricultural technology extends life. In the model, you'll see two dependency arrows from technology. One goes to the death rate, which is called rewilding, and the other one goes to CC, which is carrying capacity. So carrying capacity goes up, death rate goes down with increased technology. Yep.
So what now? How are you going to go about figuring out which of those dire paths we're on?
You know what? It was like, this was my bucket list. I just wanted to get a paper published in Population. I never thought about what I was going to do after that. But wait, what was your?
How are you going to figure out like which one of those models is correct? Or will you?
I guess maybe the answer would be in retrospect. But you're right, there's too many. I can claim success on any future. Actually, I can't, because there is a limit. In the model, like less than 1% of those will go up to 8.5 billion. So if our population goes up to 8.5 billion, I'm going to go hide under a rock. I'd be wrong. Or I'm not going to hide under a rock. I'm going to figure out why it's wrong and do a new model.
Any other questions? I'll ask a quick one. If technology is optimized, what is carrying capacity? Can you get to
So if technology goes to 1,
yeah.
doesn't get close, by the way.
Can't.
Doesn't get close. So, I mean, I just let it float, and so that it fits the data. But in theory, if technology goes to 1, mortality goes to 0. So
people live forever.
it's not meaningful in the
Yeah.
limit. That number,
So the fitting of the data constrains it.
it gets
Existing data.
it gets meaningless.
What is your life expectancy, the optimal life expectancy you've seen in the model? Is it like over 100?
The model doesn't calculate life expectancy.
Yes.
You could calculate it from a simulation, and then you could just average it over simulations, I guess. At one point, I back calculated life expectancy, and in some of the cases where it goes down really dramatically, life expectancy goes down to like 1 year, which is possible because life expectancy is the median lifetime, and if infant mortality is 50%, life expectancy at birth is 1 year. And that's what that's what it solved to if the decrease in population was one of those steepest cases. Isn't that fun?
No more questions?
Do you have a sinking feeling?
Joe, do you want your wine and cheese?
Thank you.
All right, thank you, Chris.
Mm-hmm.